Welcome to the Flare Build Podcast. Today's guest is Jerry Marino and Bogo Giertler. Jerry got involved with the Bazel community just after it was open sourced. Early on, he open sourced rules and tools to make Bazel work with the iOS ecosystem. On GitHub, he's a maintainer of iOS build components and tooling, but his main focus is Rules iOS, a Bazel rule set for iOS development. Jerry currently leads the iOS Bazel build team at Square. Bogo has been involved in the iOS build community since leading Dropbox's transition to Buck in 2019. On GitHub, Bogo maintains ARM64, a tool for deploying legacy iOS frameworks on modern Apple Silicon devices. Bogo is currently working with the platform team at Reddit, slowly moving Reddit's iOS app to Bazel. Now over to your hosts, Tatiana and Zach, the co-founders of Flare Build, the first consultancy and product-based company focused on Bazel.
Today we are joined by Jerry Marino and Bogo Giertler. So today we are really excited to talk about the recent changes that have come down to the Bazel iOS ecosystem around ARM support, which has landed both in Bazel, as well as some of the challenges around making ARM work with the simulators. Lots of issues here that anyone working in the iOS space will be familiar with. So the first topic that we're going to talk about is actually a mechanism that was created initially by Bogo here to allow us to make use of ARM binaries that were created targeting really devices and make use of those for our simulators, because again, anyone working in the ecosystem will just be aware that the vendors tend to lag a little bit here, and we'll jump into that a bit. So I just want to go ahead and maybe hand it over to Bogo to sort of introduce the idea here, talk about maybe the whole genesis of it and how he created it, and kind of take it from there. So Bogo, over to you.
For sure. So you might be familiar especially when you got your first M1 Mac, probably somewhere towards, the end of 2020, that if you try to build almost any app that contained third-party frameworks, you would get a linker error from Clang indicating that the object was built for incorrect architecture. So the way I ended up running into it is that I was working on a side project that was leveraging the Spotify SDK. And I believe that SDK actually has been deprecated at that point. So, there was no chance for support from the mothership. And I just couldn't build it on the M1 Mac. And the only other option was to basically launch Xcode in Rosetta at that point. And or what I learned later, to quite significantly modify the Xcode project's settings to just build for x86. So, I was in a pickle, and I really wanted to build this project on my M1 Mac. So I had to get around to it and get it fixed.
Great. And so to unpack that a little bit, if you were to just build for x86, you wouldn't actually be able to run anything on your M1 machine. Is that correct?
It's not exactly correct. I think there is some FUD around this, because basically the compiler is not some kind of a magic CPU whisperer or a validator that the code actually works. It takes the code and it outputs the binary objects that can be run by a specific instruction set. So in case of, the SwiftC or, anything that runs on top of LVM, you can cross-compile with very, very low, if not at all, performance penalty to another platform. The running part of it, that's a little different, because, you could build some archaic CPU on your M1. You wouldn't be able to run it. For x86, Apple does ship, Rosetta 2. For M1, so you are able to run an x86 binary on an Apple Silicon Mac. There is, however, a penalty on the emulation part of it. That's not very, very significant, especially if you're running on a pretty beefy M1 Mac, but it is there. So trying to set up this tool chain, trying to set up this kind of development experience, was not something I really wanted to do.
Right. Yeah, obviously, I don't think anyone likes the idea of using Rosetta, especially. You finally get this M1 Mac, you're excited to get some performance increases. You definitely don't want to just slow yourself right back down and end up maybe even worse off than you were on your Intel machines. Yeah, totally understandable. Yeah, so obviously that, sort of led you down the path of really digging into this a bit deeper, and then, of course, creating your blog post and eventually open sourcing that little tool. So do you want to maybe walk us through kind of what that process looked like?
Yeah, for sure. I was initially a little bit confused. I have never, worked directly with the kind of binary code and the aspects of kind of like how the code is actually being executed on the Mac or iOS device. So, the first idea or the first hint I got for that being a possibility was actually when I believe even Apple showed up during the WWDC where Apple Silicon was introduced. They showed off ability to run the iOS apps natively on macOS. So my kind of early observation there was either they're running some kind of virtualized VM and, you're just getting some kind of remote view controller projection, or they're just basically running as pieces of native code on the system. And I believe the DTK that Apple shipped was A12Z system on chip that was originally used for iPad Pro in 2020. And that SoC did not support virtualization. So there was like a pretty strong hint that this is probably just binary compatibility and the linking magic on Apple's side. So, when I got my M1 Mac, I did try to figure out what actually happens. Install D, which is the process that ends up taking the IPA you want to install on your Apple Silicon Mac, does some weird magic in wrapping up, but it seemed like it's basically the same code that you would be executing as on an iOS device. And you could see that by just comparing, the binary assembly contents in something like Hopper, that basically the contents of the frameworks directory, let's say, in the IPA that you sideloaded is basically the exact same thing as the thing you built with originally for the platform. That platform being ARM64, right, for iOS specifically.
Yeah. And then maybe we should dig in a little bit to how the tool actually works, because it's doing a few additional steps, right? Like it's not as simple as just reusing these things. Like we're actually making some changes to the binary, right? So you want to talk about what some of those specific changes are?
Yeah, for sure. So ARM as a architecture, it's almost as old as, x86. I think ARM1 shows up in like 1985. The current incarnation of ARM is, I believe, ARM v8. And that thing shows up in like 2011. So that's a pretty remarkably long, consistent period of time to have the same instruction set. There have been extensions, and I think M1 is like ARM v8.4 or something. So basically on the binary code level, in terms of the instructions that are being executed, the code is being executed on Apple Silicon and the code is being executed on your iPhone, your iPad. In some ways, even Apple Watch, although that is like a weird version of ARM v7 with 64-bit extensions, then on a binary level is basically the exact same code is being executed. What is different is basically the match-O file organization. And just specifically, there's only one place where those things truly differ. So if you are not familiar with how match-O files are arranged, they basically start with a magic word that indicates what architecture you're going to be running. And then you have a bit of a header and a list of load commands. And those things are basically meant for LD to, infer how it should be working with the binary that you're loading currently or linking to another binary. And there is one specific command that has been present in previous versions of iOS, which is lc version min iPhone OS. And there's another one, lc build version. And basically, depending on which version of iOS you're working with, I think if you're working with the slightly more archaic versions, it's lc version min iPhone OS. The modern versions use lc build version. You can indicate to the linker which specific platform this binary is meant. And you can, by actually swapping, I believe in lc build version, which is literally one number from, I think, 6 to 7, you move from iPhone OS to iPhone OS Simulator. And for the older version, you need to modify your binary slightly. That also involves, modifying offsets. I do go into this in the blog post at length, but basically, I believe the original command is slightly shorter than the command you want to inject. So, you suddenly need to modify the table of contents of the binary. So, the loader kind of knows where to perform jumps in memory, where it's supposed to read the instructions from. It turns out that once you kind of start dissecting the binary, the pattern, the way they're assembled, has been very, very consistent for something like 20 years. I think the current match for Mac OS standard has been present since Mac OS 10.6. So it's actually remarkably consistent. And once you start decoding it, it all makes sense on how things are organized and how you can edit them without affecting the binary too much.
And I guess I know you touch on this in the blog post, but really the big thing here is that the macho binaries are position independent, right? So eventually the part of the program that we actually want to run is the text segment that is just kind of maybe getting moved around. But in theory, we're just getting in there, we're hacking the load commands. And then after that, the sort of the text segment just stays intact. Is that a correct sort of summary?
Yeah, I believe position independence shows up in macho binaries or macro binaries. I actually never know how to pronounce it correctly. Shows up, I believe, with the transition to LLVM. It's actually like a more recent addition, but that's correct. Basically, once you indicate in your load commands and kind of your table of contents where the right segment is, those segments are position independent, so they basically count from their beginning. So any kind of jumps, moves, anything that involves like a specific binary address is kind of safe to relocate.
So basically, the ARM API, these CPUs, ARM has this like API, and they kind of say that like, you can run code that's written for one ARM API, and it's pretty much guaranteed to work on all the other APIs. So the API that's on these 64-bit devices is pretty much consistent across. So at a technical level, from the like CPU's perspective and instruction set, you got the same ISA across all the platforms. So at like a very low level, the code can actually work because of the CPU ISA. However, there's like concerns at the build system layer, and the linker actually has an error or a warning, depending on the way you invoke it, to give the developer an error or a warning to basically prevent them from linking in the wrong kinds of static libraries into the main executable.
Cool. Well, yeah, I mean, actually, maybe Jerry, since you have done a lot of work, obviously, in this space, I'm curious, like, before Bogo's tool, I'm curious to hear what kind of hacks you were up to, if any. So maybe let's start there.
Yeah, I can give a rundown. Well, basically, I had a different introduction to this problem space than Bogo did. I came in probably like a year or so, like after it was totally released. And I was looking at it in maybe a different light. I was kind of like, well, they've already got this like API, and these binaries are effectively the same. Like we've been doing another interesting thing for the last like decade on iOS, which is that we run x86 builds of iPhone apps on the Mac inside of a Mac app, which is a simulator. So I was kind of like, well, they've effectively got like a very high level runtime to like deal with a lot of the code that the developers write. It's pretty abstract. The API is effectively the same on an iPhone as it is on a Mac now. And these developers have all these dependencies that are compiled already. How can we like get those things up and running? That's kind of where I came into it. And I was more of like looking around, and I posted on Twitter and asked people if like anyone had a solution to this. I actually met Bogo offline because of this.
Yeah, nice. Yeah, I think definitely. So the tool is out there. In theory, it works. I know that in practice, things are never as simple as all that. And there's plenty of other little issues that we've all started to see as we've tried to adopt it. So yeah, I mean, maybe we could talk a little bit about what it looks like in practice and what sort of some of the issues are that are arising. I know that like a lot of other folks in the ecosystem would say that using this is a little risky, a little crazy, maybe even. So maybe Bogo, you want to tell us, you developed this little hack, worked great for your side project, made an awesome blog post. But what does it look like for you? Like, have you adopted it at a major scale on any production apps? And like, what are the unexpected edge cases that have inevitably arisen?
Right. That's a great question. And yeah, it definitely came out from like a side hack, right? I kind of did not expect, I was like, yeah, it's probably, useful to like 5 companies and, like 5 frameworks out there. And it did have a little bit more of the adoption than I expected, which is great. But I did use it, and I believe it's still being used at a startup that I was helping out with for a while. And that startup is using the Spotify SDK. So, for them, it's very important to be able to run with, local builds that can kind of run the ARM64 deprecated SDK. But yes, I did definitely run into an issue, I believe, when Xcode 13.3 came out most recently. There is a thing in the load commands called, I believe those are zero fill sections. And the LD in Xcode 13.3 actually got much more strict about enforcing the location of the zero fill sections. That's something that I originally did not even I was not even aware of the existence of those sections. Their code is like hidden pretty well in like the match like header files. And yeah, I think those sections must have been, excluded from the offset. But that basically meant that any deployment of this tool that was modifying a framework that had, zero offset sections, like you needed to basically redo that deployment with updated code, which is not ideal. As you might have seen in the blog post, it's a pretty involved process where, you have to unarchive the library that you're working with. After you unarchive it, you have to kind of edit every single binary file separately. And, you can run it with like a nice little bash script. Or you can wrap it up as a Bazel rule, which, makes things obviously easier, which, you obviously should use Bazel. But yes, it's a thing that, I would not have expected will be an issue, but, it became an issue. And, fortunately, one of the community members have addressed this pretty quickly with pull requests, which is great. Also shows you the power of community. When you step away for 5 seconds, somebody will come and pick it up. But yeah, that was something I've definitely seen as a problem. And I believe there were folks trying to run ARM64 to SIM on the Google Maps SDK, because Google for quite a while has not published the SDK for ARM64. And I believe that might have been related to Bazel toolchain, which Jerry, I'm sure we'll talk about in a while. But there, I believe, have been issues with like Quartz Core, where the specific implementation, I think, that's used on macOS and the simulator was somewhat different than the iOS one. So no, those are the things you cannot really fix very easily with just a couple of flags or editing the binary. But yeah, I mean, I've seen it run in companies larger and smaller. I think Reddit is still using it as well. Things seem to be pretty okay.
Sure. Yeah. So I have also dabbled with this at a few places. We went the bash script route and just sort of hooked in to running this sort of when we were vendoring in the dependencies for the first time. So actually, I want to back up for a second there, though, because I don't want to miss this important part. So you created this tool and just had the idea to even think about it because, you were trying to use an old deprecated SDK. I think the challenge here is that, unfortunately, vendors have been extremely slow to release updated versions of their libraries. So Google, of course, in particular, has been drawing a lot of fire for this, but really everyone. I mean, I would say 90% of the pods or whatever are just not updated for most vendors. That seems to be the ballpark at large companies. The other challenge is if you fall behind at all, bumping those dependencies very frequently, you're going to be looking at major changes and API changes that inflict quite a lot of app code updates when you go to bump those dependencies. So if you're a large iOS team and you don't have a great strategy in place for sort of staying on top of those most recent updates, actually, like adopting the M1 Max is a huge lift. Even if there were binaries available for, every single dependency that you have for the M1, you still have to go bump all those dependencies. And it's just quite a lot of work. And I think that that's probably a big driver of the motivation. And that's why, so many people I think are so interested in this tool, because it just sort of helps us, one, solve our own internal issues of not having had a good update strategy in place. And two, it helps us get around the fact that vendors are also just terrible at releasing these updates. So yeah, I think that, with that in mind, that was definitely the motivation, on the projects I've been on. Is just there's definitely an imperfect support for M1, but then outside of that, these updates are just way too much scope, right? So with that in mind, we've implemented it with a hacky little bash script. Like you said, there is a lot of different steps. And so, putting that together in a bash script makes sense. Definitely long term, I agree that Bazel is the way to go. And that's why I'm so excited to talk about what Jerry's been up to with it. I think for us, some of the edge cases, we got hit by the Xcode 13 thing, but luckily, someone from the community had already had a PR open. So I was really excited to see that. I think the other thing was there's just some other little, dynamic support was something that we added, but that was trivially easy. Little things like that. Surprisingly, the tool worked.
Yeah, I think it was an interesting edge case. I believe you might have run into, and if not, it was my old friends at Dropbox run into. There is OpenCV2, I believe, that is compiled for Intel and ARM differently because of how the algorithms are specifically implemented using extensions to each platform's ISA. And I think on Intel it uses SIMD. On ARM, I think it might be implemented just directly using the Neon extensions. And you cannot really move it very easily because the headers I believe, actually assume that the simulator equals Intel on iOS. And in this case, this is not true because you don't have those symbols anymore available. So I'm not sure if you ran into it at some point, but
yeah, we did.
OpenCV2 was an issue.
Yeah, that was definitely an issue. In our case, it was just like, okay, go get the right binary. So in that case, there was no real reason not to just grab a binary built for the right platform in the end, rather than trying to convert one. It was just like maybe going a little too far with the tool rather than fixing the problem correctly. So that's why we didn't really pursue it too much further, because it was just a matter of like, okay, well, we can just grab something built for the right target initially and be done with it. And so that was where we went. That's definitely an edge case to be aware of. That's one of those things where I think that's why it's kind of hard for me to give super strong advice on whether or not people should use it, because it really depends on a lot of internal variables, right? Like, do you have any libraries that aren't going to convert? Are you far behind on updates? Like, what does that all look like, right?
I actually ran into a lot of interesting situations with this program. I tried to use this thing at a very large scale with many, many different kinds of dependencies, inputs in programs. And I think the biggest one that you'll find is that, first of all, you need to have PIC in order to shift down the bits inside of the Mako files. So if you don't have PIC static archive, it's not going to work. So the first one is it's definitely a concern of the linker to permit linking in these Makos. And there's a code path inside of LD that you can set a flag that will allow it to link. However, it just spews a bunch of warnings, but you can do that. So that's one way to get around the non-PIC thing. The other one is to use a different linker or patch a linker to not have that warning. I wish that you could just turn off the warning, because it's I have a hermetic build system. I'm deliberately linking in object files from device here. That's accepted. The other funny edge case is on, I think, Xcode 13, LLDB added some code to look up SDKs directly from dwarf info. And so basically what was happening is if you had one of these device-built binaries in it with dwarf information inside of it, LLDB would totally break. It wasn't actually a problem for most people if they had these third-party SDKs that don't ship debug info. But if you had other kinds of dependencies that had debug info in there, it actually totally blew up the debugger. I had to figure that out. I think there's been a lot of patches to LLDB since these issues came out. They really refactored it. But what I'm doing right now, and I can talk more about in the Bazel thing, is I'm actually shipping out the debug info for those executables. There's a way to fix that. And the other issue and edge case that I hit in some use cases was this compatibility shims that you can conditionally link in. That was another one. But other than that, it's been pretty reasonable. And I think it's pretty a normal thing that you would do in computing. You have these binaries in these files. You just want to run them on a machine. It's pretty regular. But the linker and the tools are having warnings that are hard to turn off, even if you want to do it.
Yeah, I think what's worth to underline here is that when you ship to the App Store, I think Apple will require that you build with the newest or the new enough toolchain from Apple. You cannot use your own custom Swift compiler, for example, that you got from Swift.org to ship to the App Store, but you can use a custom linker. You are not beholden to using the LD that ships with Xcode specifically. You can use ZLD, you can modify your LD. So that's actually a really great point that, for a thing that's actually managed by linker, you can circumvent it by just circumventing the linker.
Yeah. Also, for this one, which is interesting, because it's not actually a production thing. That's a funny bit here. We're not actually shipping a production simulator built to the App Store. So any objections to using something like this, which I think at a fundamental level, it is a pretty normal thing to just have some binaries and link them in and run them. But it's not we're not shipping anything to a customer or in the App Store really that has this thing on there.
Yeah, that's a great point. I think basically when you are preparing, because what you need to use for this kind of solution is the XC framework, because basically the only way you can express this kind of more complex kind of platform / CPU arrangement. And if you're not familiar with XC framework, that's a way of organizing frameworks that was introduced, I believe, with tvOS, because tvOS had a different set of system frameworks that you would have to link against, but it had the same CPU. So you couldn't just have a flat binary anymore with just x86 and ARM. So, in the XC framework, you can very clearly specify that this slice is going to be used for, simulator ARM build. And you're never going to see those zeros and ones in your App Store release. Now, my reference was specifically more to like, if you organize your tool chain in a specific way and you don't want to like switch between a release and internal, which again, if you have Bazel, it's pretty straightforward to just, have this like config change. If you don't have Bazel, like good luck. but yeah, that's XC frameworks definitely help a lot with also kind of hermetically separating this potentially weirder but normal piece of code from the thing that goes to the App Store.
Yeah, I don't know if you did this on your blog post or it's on in the blog post that I posted up, but basically for the last 20 years or something, these Mako files are partitioned out in a fat file, which is basically a fat file is like all these different slices of machine code inside of an archive or a Mako file partitioned by the architecture slice. And so that works great when you've got something like x86. All the iOS developers usually assume that like x86 in an iPhone thing or an iPhone release artifact meant that it was for a simulator and that ARM was for device. But now these fat file idioms that people have been using for the last 12 years are no longer applicable because you've got an ARM slice for a device and you've got an ARM slice for a simulator. So they needed that like packaging format that you discussed to like, deal with this. But I think it's actually more idiomatic and more like of a better packaging standard because you can put a Mac binary inside of an XC framework now and say, hey, like this is for Mac OS. And you can ship like a pretty big SDK directory that has everything in there with like a pretty reasonable format.
Yeah, XC framework definitely makes life so much easier, especially if you work on multiple Apple platforms and you want to ship your framework not only for iOS, the simulator and the device. And I mean, we're not even talking about ARM like Apple Silicon implications. But if you want to do like tvOS, watchOS, HomeOS, I don't even know if people ship stuff for HomeOS, but all those things you can ship them in a single .exe framework, which would just makes life so much easier. But it does require a little bit of messaging in Bazel to actually work.
Yeah. That's actually a great point. Consuming XC frameworks, even in Bazel, I don't think that's landed. I know the PR is open for a while. I haven't checked in on that recently. Maybe it finally did, but I've applied the same patch that implements XC framework support like 10 different places. So hopefully that's finally landed. I should check in on the PR. Maybe one of you guys knows.
It works in Rules iOS. I haven't seen the other.
Just saying, we use it at Reddit for XC frameworks, definitely. So it works.
In Rules iOS.
Yeah. So so actually, like, there's we could talk at length about this. I don't want to derail it too much if we get more in the Bazel, but basically, there's a lot of logic and things that we have to do inside of Rules iOS to actually like link applications, and dealing with XC frameworks specifically has layers of logic in there to get these XC frameworks to do stuff like actually work with Bazel, allow people to import them, read them into our virtual file system, and also do stuff like, hey, like you've got a device artifact, let's like make that work with iPhone simulators. So we kind of have like this rule in Rules iOS where you give it a XC framework and it just kind of takes it, and based on whatever features you have, it's just going to work out of the box.
Yeah, we can definitely get into that a bit more. And maybe you'll have some critiques for my pretty naive implementation, which requires a human to tell the system which slice it should be looking at in there. But yeah, definitely curious if you automated that at all. That's very cool. I actually tried to implement having the build system just figure out which binary to grab based on conditions, but there's not really any, like basically, of course with Bazel, you need to know ahead of time what the inputs are, and we can't do anything dynamically. It was kind of a dead end when I worked through it, simply because the internals of the rule sets all expect to have file handles, not just like the sort of more opaque folder artifact, the tree digest or whatever. So I kind of gave up on it, but definitely curious to see if you guys have it sort of automatically working.
Yeah, absolutely. So, I mean, let's talk about it at like a higher level. Like, the XC framework package is a specification to import external dependencies. And for that reason itself, I think that actual instantiation of Bazel dependencies is actually handled by something like pod to build or another tool that reads in package description and then generates a Bazel rule, which actually makes it a very easy problem to deal with and a super idiomatic thing where like, oh yeah, we can open up the info plist and we can look at where the slices have to go and do whatever we got to do and then plug them into the build system and then kind of like add logic inside of Bazel to handle this. And that's how Rules iOS works. You basically give it a dictionary of what slices you want and where they're located. So you can either enter that dictionary by hand or like code generate it somehow. But I think, does that kind of align with like what you hit, Zach?
Same thing, yeah. So yeah, I couldn't find a way to get around providing the dictionary that's basically like architecture and OS or whatever, as a key. And then we can go find, deterministically find those slices, right?
Yeah, I mean, honestly, like the other thing that I've been thinking about is like, well, we kind of have these like idioms in Bazel of pulling in external dependencies. So it's probably best to have it handled there. If you wanted to make a very like user-friendly rule that was easier to give to developers and you can just be like, oh yeah, glob star this thing and it's just going to chug it and do whatever it's got to do. What I was thinking is you could have a Bazel rule, kind of how these other Bazel rules work that take these frameworks and set them up to work for a simulator. You could actually process the info plist inside of Bazel and then return data to upstream rules that determine where the headers go. Plug those into the compiler invocations, the right set of headers, the right module maps, and actually express the right linker input in the same way that we're dealing with these linker inputs in Bazel in general. So I can talk more about like that, like how we're dealing with this in Rules iOS if you want.
Yeah, I don't want to go too far off track just yet because I think that so obviously XE frameworks are related to the ARM stuff. And I just want to make sure that we focus in on what you've done to make, this tooling actually work well under Bazel. And then we maybe can come back to XE frameworks in general after that. Yeah. So obviously, like you said, you've been trying to make this tool work kind of at scale across a large, diverse set of inputs. But so I guess maybe tell us a bit more about how you've operationalized that. If I'm not mistaken, this has already landed in Rules iOS, where you already have some sort of first-class support for taking x86 binaries or libraries rather, and making them work for the ARM devices. So what does that look like?
Well, my first tool was Jira. I wrote a Bazel query and was like, hey, like let's try to at least like get all the ones that are like already supporting the simulator done and update those first. So I actually wrote a Bazel query to find all of the statically or dynamically linked build inputs. And because Bazel's a hermetic build system, we already know what it's linking. It took me like 5 minutes to write a Bazel query to like dump out all the things that had to be updated. So that was kind of my first order. But I would say like next steps was to get this thing working in Bazel. Everyone was using Bazel 4 at the time. And there wasn't like great support for ARM64 in Bazel 4. It needed like a new CPU type. Rules Apple needed updating. There's an impending transition to platforms in Bazel, which is really exciting. That's going to be a better solution for all this stuff. So anyways, like back in the day, I was like, well, I got to get this thing working on Bazel 4 with all the existing rules because this thing has to work like yesterday. I can't wait for all this stuff to be done. I was like, what's the easiest thing I can do? The program already builds on x86 in Bazel. The target CPU architecture is a higher level abstraction that we can just make x86 do whatever we want, that CPU in Bazel. So Rules iOS has a toolchain in it. It's actually being deleted now because of Bazel 5, but there's a toolchain in Rules iOS that took the x86 architecture and target for simulators and ran it as ARM64. So it was a very small change. I basically just reworked the Bazel rules and toolchain to like deal with it. There's definitely some edge cases you got to watch out for. But that toolchain basically got it up and running really easily without Bazel 5 and without updating Rules Apple. And then later Bazel 5 was done and like all these rules were done. And so that toolchain is like, it actually works on Bazel 5, surprisingly. The toolchain is kind of like not necessary anymore. So we just like select on the CPU for ARM64 basically for simulators and do all the magic stuff.
So what does that look like in relationship to the ARM64 to sim though, right? Like you created a rule set that actually does invoke that tool over some of the binaries, right? So how does that? all work.
Yeah. So like if you can like build with Bazel on ARM64 in general as like a dependency to doing any of this, then the next step is to like look at the build system inputs and make sure that they're all exactly like right for the target. So before the assumption was that you had these fat binaries and you could link them wherever you wanted, but that's effectively different now. So the main thing was like, well, what's the target architecture we're compiling for? Let's kind of look at the build system inputs. And then if they're not what they should be, then run ARM64 on them or provide a linker flag that treats it as a warning and then like do all this post processing to it. And then finally feed that into the linker. So it's kind of like, it's a very higher level thing where like we look at these inputs and then we run ARM64 on the inputs if they have to run and then just hand it off to the linker. And yeah, that's really the gist of it.
Cool. It sounds like it works pretty well. Pretty hands off for the user. I'm curious. Like, I wonder how deterministic it really is. Like, it sounds like there's a lot of conditionality going on under the hood, right? So I guess like the experience of running what might look like the same target if you're on x86 versus on ARM, I guess you're in the end, you totally different set of steps is happening, and then obviously you're getting a different output in the end anyway, so maybe that's fine because it's building for a different platform. But I think that's an interesting thing to think about, that maybe there's like a bunch of intermediates that run that's kind of opaque to the user.
Yeah, it's all fully deterministic and reproducible as well. Everything has an answer. In Starlark, it's not Turing complete. The logic is effectively deterministic. And yeah, I mean, it's pretty cut and dry. Like it was easy to transition from that thing I was doing on Bazel 4 with x86 to get it up and running, and transitioning there's like basically a bunch of select statements that deal with some of that fallback stuff. And then at build time, it can like do stuff like introspect a binary and then actually feed that into the linker. So we have an aspect, which actually like you can set up this aspect and rule to enumerate all of the inputs to a bundle. And this aspect will basically create actions with all the inputs. Or excuse me, it's actually a rule. The original version of it was a rule that had an aspect looping all over the dependencies and sitting between the bundling rules and the linker rules to like do all this processing, and then basically feeding all those inputs to the linker invocations.
Cool. I want to drill in on the linker stuff actually. So you mentioned obviously changing the flags around to the linker depending on the scenario, and then also maybe even using a different linker. So what's the current thinking around like, which linker is Rules iOS using? Obviously, a lot of folks in the community use ZLD for development, and then LLD is making a big splash right now. So, kind of, what's your thinking on that, and how does that relate to making ARM to SIM work?
I mean, let's see. If you have a linker and you just allow it to link in device built static object files, then you won't have this problem. Right. So it's kind of like, like you can just patch a development linker to not have the warning. And actually, it's an exception by default in the current version of LD that ships. It's a fatal exception that you can't continue to link. So if you have your own linker, then you can override that. However, Rules iOS, the ability and functionality is a conditional feature. So you don't have to use it. You can basically turn it on or off. And Rules iOS is like, will work with any linker. Like it's kind of like it uses the regular like Bazel tool chains to determine like what compilers and linkers to use. So if you want to use like ZLD or like Apple's linker, you can do it. It's totally up to you, whatever works for your application. But by default, it works with the like basic linker that ships on the tool chain.
Cool. All right. Well, so I guess I'm curious to hear, Bogo, have you adopted Jerry's wrapper around your tool yet? Or what does that look like? Do you have plans to go there? It sounds like you're already using Rules iOS. So is this something you're taking advantage of?
So, I mean, Rules iOS is fantastic. Like, I think it's literally the only reasonable way to like deploy Bazel with iOS these days. I think we have not used that specific wrapper just yet. I think majority of our third-party dependencies have already provided Apple silicon slices, so that's not strictly necessary. And I think for whatever is left over, we use the hacked binary for now. But yeah, I mean, that's something that definitely should be used if you decide to use that hack specifically. Doing it via Bazel wrapper or wrapping it in a macro is like the much, much more straightforward way of going about it than doing it by hand, especially if we discover in the future that we are missing some section or we need to modify that tool. And, you don't need to go back and unpack this binary again or library again and, run the tool in every single binary in the archive. You just bump your rule and everything magically works. I mean, not actually magically. It's all very deterministic, but
it's deterministic magic, right?
Yeah, exactly. I think that the whole thing that to me was a very interesting part of the entire experience of both with, ARM64 and, working with Bazel is I think it's very easy to just treat a black box in your life, be it like how the code executes or how the code builds or how the code is linked as non-deterministic thing that you just don't want to touch and kind of really compartmentalize it in your life and just like not think about it. But it turns out all those things are like very well designed and people have been working on them for a long time. And like once you actually peek under the cover, the intricate mechanisms are actually quite awesome. So I do recommend peeking under the cover because it can really teach you a lot.
Yeah, absolutely. Not for the faint of heart, though. Actually, one other thing that I forgot to bring up when we're talking about like edge cases that have arisen, wasn't there something around debug info that I think we all overlooked and it kind of came and bit us all? I don't know who wants to talk about that. The short answer here is just we need to strip these objects, right? But so maybe Jerry, like, is that something that you've also put into your like internals? That's probably part of the process, right? You need to strip that debug info.
So yeah, like LLDB, there was some code in Xcode 13 added. I don't know if it was Xcode 13 or what, but in LLDB on GitHub, there's code that like looks at the dwarf info inside of the binary to select the SDK so that when LLDB has to process and compile Swift modules, it was using the actual SDK inside of the dwarf information, which was for a device, right? So the easy answer is like, if you have dwarf info, you can do one of two things. You can actually patch the dwarf info to have the right SDK in it. You basically just need to write a dwarf patcher that's similar to ARM64 that actually goes into binary, patches that dwarf segment. Because I really don't have to like look at debug information in these things. It's kind of like an obscure thing to like look at the debug info for these. Most people use a DSIM. It just strips them out. Like the iOS rule basically will strip out the dwarf information by just using strip as part of its linker pre-processing rules before it feeds it into the executable linking step. So it basically, that thing just kind of chugs away. It does like a lot of other magic too, but that's like one of the things that it does.
Yeah, that's great. Yeah, actually, I would be curious to see what the work would entail to actually patch the dwarf info, but sounds like it's not really worth it. I mean, I don't know. Curious, Bogo, if you thought about that at all.
To be honest, not something that really crossed my mind. I think if you need to breakpoint inside a third-party framework, you might have larger problems than that.
Right.
So, but back in the day, early on, like people used to have to patch dwarf info to get it to work with remote build in some scenarios.
Interesting.
Actually, in the Bazel ecosystem, like really early on, like, we had some dwarf patching code. It's out there. I can link it up if people are interested in whatever. But basically, the gist is that like if the SDK is like smaller in length, it's really easy to just replace that entry and then null terminate the string, and the upstream dwarf reader will do it. If you go from like one string that's super long to one string that's super short in that binary, the upstream code just like chugs away and reads it.
Right. Cool. So yeah, we touched a little bit on some of the changes architecturally in Bazel that were kind of inflicted by the Apple Silicon thing. And I know that I don't think any of us work too directly on that part of the Bazel code base, but I know that Jerry definitely has some insights there. So maybe now's a good time to kind of talk through a little bit of that stuff. So kind of at a high level, at least from an iOS perspective, yeah, maybe let's dig in a little bit to like what those changes look like in Bazel 4 and in the rule sets, because obviously this impacted rules iOS as well as the other rule sets and the changes to the Bazel core. So Jerry, you want to take it away?
Yeah, I mean, timing is everything, right? And for me, I had the challenge to get this thing running on Bazel 4 because Bazel 5 had a lot of things and release blockers that I had to have fixed. And so it's kind of like get it working on Bazel 4 first, and then like update it to Bazel 5. And we had this like tool chain that could like effectively treat x86 as like ARM64. But in Bazel, like there's this idiom in the C++ rules, and a lot, even the Swift rules have their own tool chain, but effectively you have a CPU, which is an idiom inside of Bazel that is like kind of a higher level thing. Like, oh yeah, I'm targeting this like CPU. And the rules can implement a CPU in whatever way that they'd like. But generally for the iOS rules and all the dependencies will say, oh yeah, like they previously assumed that like ARM64 was for device and that x86-64 is for simulator. And so there's a couple of interesting things here. The first one is that like you can no longer like disambiguate simulators and devices amongst CPU anymore. You have to have a higher level abstraction. Abstraction in Bazel that people are excited about using here is the platforms abstraction, which is effectively a way to vary a CPU, which will better accommodate something like this. But the Bazel 5 in its current status has a new CPU type, which we also handle in Rules iOS. We have the CPU type, and it's basically a hack to adopt this without having the full platform thing implemented. It just has a prefix on the CPU type. So instead of ARM64, it's sim_ARM64.
Yep.
And that's all. That's all the tools disambiguate the CPU type. So pretty simple.
Luckily temporary, because platforms are eventually coming out for, in theory, for every tool chain. So we'll see. Excited to see that happen. Yeah, that's definitely an interesting little hack that made me laugh when I saw it, because I kind of immediately understood what was going on. But yeah, you do what you got to do. Okay, is there anything else you want to drill into on like the Bazel side of stuff here and what some of the implications are? As just again, I know we're just mostly just consumers.
I mean, let's see, like the tools themselves, like the actual simulators themselves are like one thing, but I would say like there's a whole other bag of problems that are involved in this kind of transition to like ARM in general. The other ones are like, well, a lot of this code like runs differently on like a device versus a simulator. So like if the developers have like conditional compilation or like different dependencies, the code actually runs differently. So that's one. And then like all these like other kinds of programs that is involved in like tooling, like all these interpreters like Pythons and Rubies and other kinds of programs themselves, like all have to be like supporting of this. So yeah, it's definitely interesting, right?
Yeah, definitely a lot of big changes.
I feel like at the end of the day, like the easiest thing is that like the developers are like using a simulator, and it's so much easier to just do that thing than try to like do other things. And getting everything working natively was like really just a matter of dealing with the code that was operating differently on a simulator, these like SDKs. And I don't know. I feel like it's a good way to deal with it.
So what you're saying is that actually ARM, like the ARM to Sim stuff, is like the least of your worries when you're making the transition to M1 and Bazel on a big build.
No joke. Like,
yeah. I mean, look, it's like definitely a blocker if people are like, this linker is like not linking in this source code. That's definitely a blocker. You know, I think what are some of the other things that you all ran into on like the transition in general?
Yeah, on my side, it was definitely like XC run and like running tests as they were built for, I think if you were building them for x86, but you wanted to run them on M1 Mac, you would end up with like XC run not being happy with the slice or not being able to run it correctly. So you needed to like slice XC run into having like an ARM64 and x86 slices separately, and then just use the x86 slice to run x86 code. So, the forking doesn't end up going through Rosetta. As Jerry said, like actually like ARM64 to Sim is like cool project, but there is so much more to like make sure, especially with Bazel 4, that you can, run your builds and your tests on M1 Max happily. And I mean, don't even get me started on like M1 Max having a very, very different, I believe, part score implementation than x86 Max. If you have snapshot testing in your project, most likely your M1 Max snapshots are going to be different than your x86 snapshots on like a pixel level. So there's even issues you need to address on that on point of like snapshot tests, right? So it's a whole universe of pain just waiting for you in the Apple Silicon transition.
Yeah. For us, a lot of the stuff we've been dealing with, it comes down to compute. Think about remote execution, right? Like, you've got maybe you've got a farm of the x86 Mac Minis somewhere in a closet, and then you can't buy those anymore. They don't work with your M1 builds for developers that have switched. It's just a whole nightmare.
Could you cross compile on those x86s for M1? I think you could, right?
it just gets to be a huge challenge, right? Like the more like trying to do cross compilation in remote builds, I don't really. It's best to align platforms as much as you can, right? And just kind of avoid some of those issues. Yeah.
I totally forgot about this, by the way. Yeah, like actually making this thing work with like CDN or like however you're going to cache them is another actually really interesting thing. Like I feel like you can do two things here. You can just say, oh, just dupe over the builds for the Apple Silicon simulators because the devs are like trying to like remote execute or remote cache it against these things. Like, did you all like work at a toolchain level to allow x86 simulator builds to kind of work together with the ARM64 ones, or like how does that actually work?
Yeah, so you're saying trying to reuse the same like intermediates or something, so we don't do as much work.
I mean, okay. I guess let me like take a step back. So like say you have like a big fleet of like x86 hardware and you've got to like now all of a sudden you got to cache it against the M1 hosts. Well, you can do two things. The first one is you can like allow the x86 hosts to produce ARM64 simulator builds and artifacts and push those to remote execution or the CDN. And then the developers on M1 machines can cache hit the artifacts produced from the x86 machines. Or you can just say, hey, like buy a bunch of M1 machines and just don't worry about the toolchain level solution.
Yeah, so I think there's enough concerns that we're just making sure the platforms just align, right? So we just make sure that like if you're on x86, you land on the x86 cluster, and then if you're on ARM, you land on. Luckily, Amazon now offers the ARM machines in their offering, which is awesome. On
Rules iOS, like we actually have this problem too, and it was one of the things that I had to face with like this Bazel 4 thing. We have to get cross compilation working for M1 simulators in Rules iOS, and so like basically you can like if you're on like whatever machine you're on, you can cross compile for a iOS simulator on M1 or x86 because like GitHub doesn't have like they didn't have like a X or M1 machines to like run on. So we had to kind of solve that problem.
Mm-hmm.
Yeah. I mean, I think cross compilation is fairly straightforward on the same machine, but it just gets, when you start throwing remote builds into the mix, to me, it starts to violate some of the paradigms a little bit too much, I think. So yeah, it's something that if someone really pushed us for it, I might try to make it work, but it's something that I'm happy to avoid as much as possible.
Yep. Rule Swift actually has they now have a fat binary inside of there, a universal binary, and they have some other things. But the easier is like if you take all the toolchain inputs and make it so that it's like using a fat binary on like x86 and ARM for compilation on your macOS environment, it will actually cache it if all the inputs are like kind of different. Like you could cross compile from x86 and like target a M1 simulator and it will work kind of like how we cross compile for iOS.
Yeah, exactly. I mean, your machine is, especially in like Intel days, right? It would have no serious issues like cranking out an ARM build. And you can actually if you would compare build times, which is kind of what I was saying later, right? Like compiler is not like a magic CPU whisperer. It will take about the same amount of time to compile for x86 as it takes for ARM, plus minus, right? But this is like a negligible difference for you as a developer. And like the only penalty you're actually going to incur on M1 Max if you run x86 build code is that Rosetta startup time, right? Or the Rosetta, like if you're going to be deploying JIT or anything of this sort. So there's going to be some penalty there, but your M1 Mac is so beefy, you're probably going to have okay time running those builds. And I believe actually that's the approach still favored by a bunch of kind of at scale companies to just build everything as x86 because it really avoids the kind of bifurcation of like, oh, I need M1 cluster, I need x86 cluster. How do I do caching? How do I handle the frameworks, right? You can still kind of, for time being, think about everything as x86. So that's it's like an alternative solution to all of this, right? It's just to forget for a while that Apple Silicon exists as a place to execute your tests locally.
I don't know about your compiler, but mine's definitely a magic whisperer. Like, I don't know what toolchain. I don't know what toolchain you're using over there, but mine's definitely a magic whisperer.
Yeah, that is a good point though. That definitely, yeah, Rosetta is an option that a lot of people are using. You know, I don't want to cast too many aspersions on it.
I mean, Rosetta is going to go away one day, like as it did in Rosetta 1 with like, PowerPC to Intel transition. 1 year, we're going to wake up after WWDC and Rosetta 2 is no longer going to be there. So it's probably a good time to get ahead of that curve.
I was actually blown away by Rosetta 2. The integration and overall seamless experience that is in like Mac OS and M1 Max is just like unparalleled. It's I feel like the experience is so polished. The fact that you can just give these machines an x86 binary and they just run it is like unbelievable. Yep. I was like blown away. And like there's so many situations for me where I was like, look, like this thing is like 5 years old or 4 years old. No one's going to recompile this thing to work to be a M1 Max thing. They're just not going to do it. Like, I don't know how you're going to like take these old programs and try to recompile them. And I feel like the execution and like the implementation of Rosetta 2 is just unbelievable and so seamless. We actually like had to use this in like other situations where we had these binaries that like no one was going to recompile them. And actually in some use cases and some tools and programs, it was easier to use the Intel version of them than to like try to port them over.
For sure. And I mean, I think it's compared to especially the first transition, to x86, where I remember like Rosetta being like very slow. I mean, given also those were slower CPUs back then, but it was like a pretty heavy thing to run, right? Like you would definitely feel you're not running a native app. That's on one hand. On the other, like Rosetta, I think still there are issues around like text presence and plugins, cross-platformness, but like also as macOS has moved away from texts, right? Like everything is moving more and more into user space. Like the actual experience of using Rosetta with very complex software is great. Like you can actually run Xcode under Rosetta, like force it to be an Intel application on your Mac. And it's still remarkably fast. It's actually still faster than in many cases, like it running on actual Intel CPU, right? Which is nuts. And I think even to that point, like being able to run any kind of like older, like frameworks under Rosetta or other builds is just like actual iOS. I think if you run iOS 12 SDK, I think it's either 12 or 11, I would have to double check. In Xcode, like you are actually going to be running a Rosetta version of iOS. Like those SDKs were never ported to ARM64. Like the SDKs you download for older versions of iOS in your Xcode are going to be all executed on Rosetta too.
Yeah, it's pretty amazing. Like overall, like the binary compiler and all the stuff that it works with. I'm just pretty surprised by how like awesome it is, pleasantly.
So with that in mind, Bogo, why didn't you just launch Xcode with Rosetta 2 back in the day rather than going down this whole journey?
I mean, because why not? It's for me, it was really a question of, look, I can see this runs. Like Apple manages to make it work when you install IPA. You can execute those frameworks in some way. So for me, this was, like I wanted to figure out either how it works or if I can make something work in a similar way. And it turns out you can. And I think that's really like a testament to, like, as I mentioned, like you peek under the cover, it's so intricate and like everything actually, it works. It's not some kind of, magic code. It's like, it's a well-designed system that you can work with and you can reason about, and it's really awesome when you realize it's well designed all the way down.
Great, cool. Then I guess we can go ahead and wrap up. So before we conclude, maybe do you guys want to throw out any social info? Like where can people find you on Twitter or whatever, if at all?
Yeah, I can start. I'm at Jerry Marino on GitHub, and I'm at Jerry Marino on Twitter, and I currently lead up the iOS Bazel team at Square, and we are hiring. You can find a link to that into the actually the ARM64 post about how like all this stuff kind of like works in Rules iOS. It's on my Twitter. You can find a link in there. And thank you so much for inviting me onto this podcast. I really love what y'all have done with this podcast and kind of like spreading all this cool information about Bazel to the community. It's super awesome. And Bogo, thank you so much for creating this awesome tool. And those blog posts you wrote are incredible. Really, really love it. And yeah.
Great. Thanks. Bogo, how about you?
So, on GitHub, I'm at Bogo. On Twitter, I did not manage to get at Bogo, so I'm just at Giertler, my surname. I'm currently working with Reddit on the Bazel deployment there. So if anyone is interested in setting up Bazel at one of the coolest social community companies out there, just give me a holler. And yes, Jerry, I do want to thank you. Rules iOS, this is work of community, but you have so many awesome, insanely complex contributions to Rules iOS that just make it all possible for us to actually run Bazel as an iOS build system and kind of win off buck. It's great. I think it would be so much more difficult for all these companies to migrate to Bazel if not for all your work. And thanks to Flare. It's the podcast is just such a great place to learn more about how to build things, with Bazel and how powerful the platform is. It's great to be able to learn about those from somewhere else than just Google's documentation.
Great. Yeah, thanks a lot, guys. Yeah, and so hopefully we'll look forward to having you back on to discuss a range of other topics, because I feel like we've barely scratched the surface of both of your expertises. And Jerry, of course, trailblazer for the community. So looking forward to chatting again in the future with you guys. Thanks a lot.
Thank you for tuning in to the Flare Build podcast. Please like, subscribe, and tune in again with Zach and Tatiana for the next podcast in the series.